Hello and welcome to lecture 53 of the course Computational Complexity. In the previous lecture, we saw Toda's theorem. We started seeing the proof of Toda's theorem. Toda's theorem shows that any language in polynomial hierarchy can be simulated by a query by a deterministic polynomial time machine along with a query to a Sharpe oracle. Right? And what we saw in the previous lecture was that any language in polynomial hierarchy has a randomized reduction to parity set, or in other words, it can be simulated by a BPP machine with one query to a parity P oracle, parity set oracle, right? Just to for the sake of completeness, I am restating it. If k and m are greater than 0, there is a probabilistic polynomial time reduction such that any sigma k instance psi can be reduced to can be reduced to a psi, right? So the reduction outputs a psi, where a is a reduction. If psi is a true yes instance, then with high probability a psi will be a yes instance of parity set. If psi is no instance, then with high probability a psi will be a no instance of parity set, right? In other words, it is, you can represent it as polynomial hierarchy is contained in BPP with parity P oracle, and we need to go from here to this polynomial hierarchy is in P to the Sharpe. So we are weakening the base machine, but we are going to a stronger oracle, right? So BPP to P means you're losing randomness. Parity P to Sharpe means instead of counting just the parity, we are actually counting the actual number, right? So let us see how to do that, right? And this particular lecture will be relatively shorter as compared to the previous one. And so let's see what is happening here, right? So a psi is in parity set and with a certain probability, right? So a psi being in parity set itself is saying that the number of satisfying assignment for a psi is odd or even, right? And then we are saying that the probability that this is accepted, is greater than 1 minus 1 divided by 2 power m. So let's say we use, let's say, r random bits or something like that, right? And so which means 2 power r possible choices, and out of that we are saying that 1 minus 1 divided by 2 power m fraction of all the possible choices. So if you had another machine to count how many of these choices lead to an odd parity, then we could do that. So basically, so to count the number of satisfying assignments of a psi, we need one level of one counting, and then apart from that, we need another level of counting to count the number of a psi, right? Or the fraction of random strings random choices that lead to a psi being accepted. So there are two levels of counting: one for the choice of one for deciding whether a psi is in parity set, and two for checking whether this number of accepting computations is at least 1 minus 1 by 2 power m, and same for the no case as well, right? So there are two levels of counting here. So when we want to say that we want to simulate it with just deterministic polynomial time machine with one Sharpe oracle, we want to simulate using one level of counting, right? So that's the task at hand. So let's try to understand where we are, right? So suppose psi is true, right? And in that case, most of the a psi has an odd parity of satisfying assignments. If psi is false, means most of the a psi has an even parity. But most having odd means if you look at, let's say, so you can consider two levels, right? You can consider two levels. So one for the choice of a, and then another level where the number of satisfying assignments for a psi. So if you want to just, one thing that you may want to try is just to add up the number of satisfying assignments over all the possible choices of A. But then what we know in the case when psi is true is that most cases had an odd number of satisfying assignments, and in the case of false, most cases had an even number. But then even odd could be interspersed, mixed up. We cannot really tell it apart, right? Even if most cases are odd, the sum could be even or would be odd, and maybe even the yes instance and the no instance, the total sum could be. So I am talking about the sum over all possible choices of A. Sum over all possible choices of A, and all assignments like satisfying assignments of A, or all possible choice of A, number of satisfying assignments of A psi, right? So this sum may not really give us much information about whether psi was true or false, because this could be mixed up, or it could, the same value could result from the yes instance as well as the no instance. So let us try to engineer a way where this sum will tell us the answer, and that's what is going to happen, right? So instead of A psi, from A psi we will go to another formula which will make sure that the sum itself will tell us whether it's a yes instance or no instance. So in order to get there, so here we have just parity, so odd and even, right? So odd and even are mixed up, right? So they are interspersed. There is no real difference. So we want to get a more significant difference, and from that will be our starting point. So in other words, we want to amplify the gap between yes instance and no instance. Okay, so what we do here is, given, so that is our theorem 2. This says that given an input formula alpha and given 1 power L, which is just the number of or which is just L for the sake of the an input L, right? There is a deterministic polynomial time reduction that outputs a formula beta such that if A is a yes instance of parity set, then B will have -1 mod 2 power L plus 1 satisfying assignments. So think of L as some big number. So if L is 10 or if L is 5, then beta has -1. Let's say if L is 5, then 2 power L plus 1 is 64, 2 power 6, 64. Then beta has 63 mod 64 satisfying assignments, so which is very close to the 64. And if alpha is not a yes instance of parity set, then beta has 0 satisfying assignment, 0 mod 64 satisfying assignments, and this is going to create a gap, right? Or why is it going to create a gap? So in theorem 1, given a psi, we had two possibilities. One where the number of one where the probability, if psi is true, the probability that A psi is a yes instance of parity set happened with probability at least 1 minus 1 by 2 power m, which is high probability. And if psi is false, it is a yes instance with a low probability, 1 by 2 power m, right? So if given psi in theorem 1, right, we compute alpha. Alpha is basically psi and with a bunch of random strings we do some processing, right? That's what we saw in the previous lecture to get an alpha, right? And we knew that the probability of psi and the A psi agreeing was 1 divided by 2 power m, right? So let us set m to be equal to 2. So the probability that psi is true is the probability that A agrees with psi is 3/4, and the probability of error is 1/4. And R is the number of random strings used in this reduction. Okay, so what we will do is, so we have a formula, we start with psi and we have all this A psi, right? So these are generated by different randomness, and then for each of these we will count the number of satisfying assignments and we will take the total count. So let us see what happens. So if it is a yes instance, so now let us apply theorem 2. Theorem 2 is this theorem that if alpha is a yes instance of parity set, beta has minus 1 mod 2 power l plus 1 satisfying assignments, and if alpha is a no instance, beta has 0 mod 2 power l plus 1 satisfying assignments, right? Which is what I have just copied down here. So if so we apply theorem 2 on alpha to get beta, which has this condition. And what does this mean? If psi was a yes instance, most of the A psi, like 3/4 of the A psi, will produce yes instances, right? Which means 3/4 of the random fraction, 3/4 of the random choices will have alpha as a yes instance of parity set, and for these alpha we get minus 1 mod 2 power l plus 1, right? And if you add up this, let's say we add up this, we know that the number of satisfying assignments over all the different choices of A psi, right? So we know that at least 3/4 are yes instances. So it could be the 3/4 of all the random choices, right? And it is minus 1 mod 2 power l plus 1, right? And that is at least, and at most it could be all of them could be yes instances. So it's all of the 2 power r prime. So let r prime be the number of random bits r prime used in the theorem 1. So we know at least 3/4 of multiplied by 2 power r prime choices give minus 1 modulo 2 power l plus 1, or all of them give yes instances, which is minus 1 multiplied by 2 power r prime. So the number of so the total number of satisfying assignments is anywhere between minus 2 power r prime and minus 3/4 multiplied by 2 power r prime. Okay, because each yes instance contributes a minus 1 modulo 2 power l plus 1. All of this is modulo 2 power l plus 1. So it's either minus 3/4 2 power r prime or minus 2 power r prime or anywhere in between, right? And if psi was a false formula, if it's a no instance, then similarly we can do the same calculation. So we know that the number of yes instances at most is at least 0, or is 0 anywhere between 0 and 1/4. So if all the instances are no instances, then we get 0 modulo 2 power plus 1. Otherwise we could have up to 1/4 fraction yes instances. So it is minus 1/4 multiplied by 2 power r prime yes instances. So in this case the range is 0 and minus 1/4 2 power r prime. So mod 2 power l plus 1. So there are two ranges. So let us look at the entire thing modulo 2 power l plus 1, and just for the sake of easiness, for concreteness, let us set r prime to be equal, let us set l to be equal to r prime. Okay, so this is from 0 to range 2 power l plus 1, which is the same as range 2 power r prime plus 1. So yes instance could lead to minus 2 power r prime and minus 3/4 multiplied by 2 power r prime. So 2 power r prime is roughly, minus 2 power r prime is roughly midway point. Minus 2 power r prime is equal to plus 2 power r prime in the case of modulo 2 power r prime plus 1, and minus 3/4 2 power r prime gives us somewhere here. So the yes instances are in this range. The total number of satisfying assignment in the case of yes instances are in the green range, and the no instances are from minus 1/4 times 2 power r prime till 0. So this entire range is 2 power r prime plus 1. So this is the midway point. This is the midway point, and this green portion is roughly 1/4 of the half portion, or 1/8 of the entire portion, and similarly red portion is also roughly 1/8 of the entire portion. The point is that the yes instance contributes the green zone and no instance contribute to the red zone, and the red zone and green zone are disjoint, are separated. So now we can safely, so in fact I think even if you had tried L to be equal to R prime minus 1, even then we could have worked. If L was, so we would have got some, so if, just an aside, if L equal to R prime minus 1, then we would have got something like this, I think. So let's say this is the midway point, sorry, this is the midway point, this, then we would have got the green zone to be here and the red zone to be here. But anyway, even L equal to R prime works. So in both cases it works. But if L is smaller than R prime minus 1, I don't think it will work, because then I think the zones will start merging and then we will not be able to tell them apart. Right? So now all that we need to do is to take the first reduction and second reduction, put it together and ask how many satisfying assignments are there for this entire process. So even the first reduction, instead of viewing it as a randomized reduction with random coins, we have to view it as non-deterministic choices. So over all the non-deterministic choices, how many accepting computations are there? And if we can do that, we can tell which case it is. So this one counting is required. So I have just written down the entire thing here. So given the sigma k instance psi as input, so you construct a non-deterministic Turing machine that takes R1, R2, which is the random choices, as non-deterministic choices. In fact, I think I said RR, so maybe I'll just change it to RR, right? And first it builds, the non-deterministic Turing machine builds alpha using the reduction shown in the previous lecture, using psi, R1, R2 up to RR. And now alpha is obtained, and now we build beta, which is deterministic, using T and alpha, right, which is using the process T, and you accept if beta is satisfiable, right. Right, we accept if beta has a satisfying assignment. So now there are two levels. So one is the choices of R, R1, R2 up to RR, and then choices inside beta. So how many accepting computations are there using both these non-deterministic choices? So even the random reduction in theorem 1 or the previous lecture, we are now viewing it as a non-deterministic set of choices. So the two sets of non-deterministic choices, so psi and then a psi or alpha, and then we get beta, right, which is still random, and then how many accepting computations are there for each level of beta. So at the end we are counting all the accepting computations of all the betas that are generated like this, right, and you count the number of satisfying assignments and see which band it lies, whether it lies in the green band or in the red band, and that's all. So just with one counting we know whether beta is in the green or red, and beta is satisfiable, or and that tells us whether alpha was a yes instance or no. No, okay, we don't look at individual beta or alpha, right? So just look at the total number of satisfying assignments overall, right? So that tells us whether psi was a yes instance or a no instance, because the green red bands correspond to only psi, and that is all that we need. So now there is no randomness. The randomness has been replaced by just the amplification and then a one counting, just one counting. And this non-deterministic Turing machine, we just want to count the number of accepting computations. So all that we need to do is ask the oracle. All that needs to be done ask the Sharpie oracle the number of accepting computations of this NTN for the given input. and that's it, and check whether it is the green or red, and check. Sorry, whether, sorry, the green or red, and that's it. So this completes the proof assuming theorem 2. So this completes the proof of the Toda's theorem. So all we are doing is build this non-deterministic Turing machine. So building this non-deterministic Turing machine is entirely deterministic polynomial time process, right? So we don't even need to know what is R1, R2, anything. We just build on non-deterministic Turing machine. And so what is alpha? The process to construct alpha and the process to construct beta is all that the non-deterministic Turing machine needs to do. So it's like writing a program and then asking how many ways then can this program succeed. So build this Turing machine which completes the reduction, and then check and ask the oracle how many accepting computations it has. Right? So that is it. So it's a very interesting thing. All that we are doing is one amplification, going from 0 1, right, to this big 0 1. So this parity set is like 0 1 mod 2 or 0 minus 1 mod 2, and from there we are going to 0 minus 1 mod 2 power L plus 1, and that is what is giving us this big range. If it was 0 1, so if L was really small here, it would not have helped, right? If L is, in fact, L is 0 means it is just again parity. So now let us see how to do the amplification. So given alpha, we need to build beta. So alpha is like 0 1, yes instance of parity or no instance of parity. From there we need to move to 0 or minus 1 mod 2 power L plus 1. So yes instance of parity means we need to move to minus 1 mod 2 power L plus 1. No instance of parity means we need to move to 0 mod 2 power L plus 1. So recall, we in the previous lecture we had shown, given a formula phi and phi prime that has m and m prime satisfying assignments, we could build formula with m plus m prime satisfying assignments, m multiplied by m prime satisfying assignments, and a constant number of satisfying assignments. So we could do m plus constant satisfying assignments as long as it's a positive constant, right? So these are the tools that we have. You could add two formulas to get a formula which has the number of satisfying assignments is the sum or the product, and we can even add a positive integer. So given alpha, the alpha is either in parity set or not. It's either odd number of accepting computations or even number. So given a formula, so now let's try to understand. So given a formula tau, okay, consider this formula 4 tau cube, maybe I'll just move it, 4 tau cube times 3 or plus 3 times tau power 4. So think of this as, because so by this I mean that given a formula tau, we could build a formula that so let's say tau accepts 10 satisfying assignments. Now I could build a formula that accepts 10 squared satisfying assignments, right? Just by what we saw above, by constructing sum, product, etc. And similarly, I could build a formula that accepts 10 cubed. So consider the formula. This means, what I mean by this is that a formula tau prime that has 4m cube plus 3m power 4 satisfying assignments, where tau has m satisfying assignments. Right? So So that's what I mean by the shorthand notation. So if tau has m satisfying assignments, this new formula must have 4m cube plus 3 n power 4. But then this is just simpler to write 4 tau cube plus 3 tau. This is not equal to 4 tau cube plus 3 tau power 4 in the strictest sense. Okay. So let's try to understand. Suppose tau, the number of satisfying assignments of tau was 0 mod k. Okay. Then 4 tau cube plus 3 tau power 4 is 0 mod k square, right? Because 0 number of satisfying assignments is a multiple of k. Then here we are taking tau cube and tau power 4. So this is so clearly this is a multiple of k squared, right? So if k divides m, then certainly k divides 4m cube plus, or k squared divides 4m cube plus 3m power 4, right? That's all that I am doing here. Now suppose tau is 1 mod or minus 1 mod k, okay, that's the condition, minus 1 mod k. Then the claim is that 4 tau cube plus 3 tau power 4 is minus 1 mod k squared. Let's see why this is the case. So suppose let's say tau is ak minus 1, right? So where a is some constant. So 4 ak minus 1 whole cubed plus 3 ak minus 1 whole power 4, right? Let's see what each of this is. Now if you do modulo, if you expand the cube, you will get something like a cube k cube plus 3, or maybe not plus, minus 3 a square k square plus 3 ak minus 1. Okay, that's for the first term. Plus maybe I'll just write this a bit differently, 3 a square k square. So I'll just write it as ak minus 1. Maybe I'll just write a bit differently here also, minus 2 ak plus 1. So I've written it as ak minus 1 squared. Okay, so now this one, if you look at it modulo k square, I can ignore all the terms that are multiples of k square, right? So this is just 4 times 3 ak minus 1 plus 3 times minus 2 ak plus 1 whole squared modulo k squared. And this is fine, 4 times 3 ak minus 1. If you again expand this, you will see that the k square term vanishes. So what will remain is, so let the 3 remain outside, 3 minus 4 ak plus 1 and modulo k squared, and what will remain is that the 12 ak plus and minus will cancel. So this term and this term will cancel, and what will remain is minus 4 plus 3, which is minus 1. So if you started with something minus 1 modulo k, so the operation, this 4 tau cube plus 3 tau power 4, meaning which is a corresponding formula that has this many satisfying assignments. If we started with tau that has 0 modulo k satisfying assignments, the new formula has 0 modulo k square. If we started with minus 1 modulo k satisfying assignments, the new formula has minus 1 modulo k square. So from modulo k, we are moving to modulo k squared, right? And this is for any k, this works for any k. And we started with alpha being in either parity set or not parity set. So which means the number of satisfying assignments was either 0 or 1 modulo 2, or 1 modulo 2 is the same as minus 1 modulo 2, right? And we could repeatedly apply this operation, right? I could go from 0 and minus 1 modulo 2 to 0 and minus 1 modulo 4, and 0 and minus 1 modulo 4 to 0 and minus 1 modulo 16, right? Every time the modulus thing is squaring. So every time it's squaring, so 4, 16, 16 squared, 256 and so on, right? And we need to get to 2 power L plus 1, right? So, but every time we are repeatedly squaring, so we are going something like 2 squared, so 2 power 4, 2 power 8 and so on. So we need to go to 2 power L plus 1. So we need to do log L plus 1 many steps. Log L plus 1 many steps, iterations. And so we'd want L to be roughly equal to R prime, right? That's what we said here. So that this ranges, red and green ranges remain separate, right? So, and R, if you remember from the previous lecture, it was roughly the number of, it was the number of random bits, and this was roughly the size of the original formula, right? So it may be a polynomial in the size of the original formula. But but the number of iterations that we do is log L plus 1. But if you do, whenever we do one step, right, the size of the formula kind of also becomes roughly, blows up by some constant. So we do log L plus 1 steps, so there is always some constant power log L plus 1 blow up happening in the size. But that is, but since log L plus 1 is something polynomial in the size of the formula, the resulting formula will also be polynomial size in the original formula, right? And this, so which means from the original formula that we had, we are constructing a new formula which is polynomial size of the original formula, but with the amplification, right? So original was the result of theorem 1 construction, and now we have the theorem 2 formula beta. And finally, we, as I said already, we combine theorem 1 and theorem 2, and we count all the number of satisfying assignments, or we don't count it, that is counted by the Sharpe oracle, and we just check whether which range does it lie in the red or the green range. So just to summarize, the second part of the proof was just mainly this modulus amplification, where we moved from yes or no instance of parity set to the 0 and minus 1 modulus some high modulus 2 power L plus 1 by using this trick. And then after that we just cascaded these, or composed these two reductions, the randomized reductions and the formula beta. And we, after the amplification, the yes instances would result in the total number of satisfying assignments being in a certain range, and the no instances would result in the total number of satisfying assignments being in some other range. So the yes instances and the no instances are separate, from which we could tell whether the original formula, which was a sigma k instance, was a yes instance or a no instance. And so that's a deterministic machine with just one query to a polynomial with a Sharpe oracle, to a Sharpe oracle. Deterministic polynomial time machine with one query to a Sharpe oracle. And that completes the proof of the Toda's theorem. So perhaps I'll just revise, just summarize this entire week. We had basically just two results. One was it permanent as Sharpe complete, which was Valiant's theorem. Right? So we saw what was permanent, and then we saw that we could convert Sharpe 3 set into into a problem of counting the permanent, or estimating a permanent. Right? So this was a somewhat involved reduction with too many gadgets. Right? And the second lecture was a continuation of the same. So it's interesting because permanent we saw that it is only definition wise it's not that far away from determinant, right? If you put the sign here, it is a determinant. If you do not put the sign here, it is permanent, right? So the sign makes all the difference. The sign, this minus 1 power sign component. But then determinant is very nice in the sense that it allows this row operations. You can add a copy of a row or a multiple of a row to another row. Still, the determinant does not change. You can do Gaussian elimination, and all this makes the computation very tractable. But permanent doesn't allow most of these operations. So, and as we have seen, if we can compute the permanent, we can solve any problem in Sharpie, and we have also seen that Sharpie can simulate or one query to Sharpie can answer any question in the polynomial hierarchy. So that's the power of Sharpie. So hopefully we appreciate the theorem that permanent is Sharpie complete even more now. So even though adding the sign changes the complexity of determining or computing the determinant to computing the permanent so much. So this lecture 51 was just a continuation. Lecture 52 and 53 were Toda's theorem, which was a kind of involved, perhaps even more involved theorem, and perhaps one of the most involved theorems that we'll see in this entire course. That showed that a language in the polynomial hierarchy can be simulated by a deterministic polynomial time Turing machine with just one query to the Sharpie oracle. And 53 was a continuation of the same. And that's all that we have for week 10. And thank you.